In this video, we're going over the concepts of Chapter 6, Part 2. We're now going to focus on reactions of monosaccharides. Monosaccharides can undergo a variety of reactions. The first of which is a self-reaction, or what we like to call in chemistry an intramolecular reaction. Intra means within molecular, the molecule. And let me explain how monosaccharides can undergo a particular intramolecular reaction. Now, we are familiar that monosaccharides, in general, we can draw them using a Fischer projection. And in this slide, you have the picture for the Fischer projection of D-glucose. Now, there are functional groups that we are familiar with that are important in this molecule, and that includes the carbonyl functionality, that in glucose is an aldehyde, and we have a series of alcohols. But for this particular reaction, we're going to focus on the OH group that is in the last chiral carbon, that is the farthest away from the carbonyl. And I'm going to highlight it in green. So what happens overall is that specifically molecules or monosaccharides that have a carbonyl functionality like an aldehyde or a ketone can actually cyclize to make what is known as a cyclic Fischer projection. And you can observe here that overall what happens is that the oxygen in the OH binds to the carbon in the carbonyl, and then the oxygen that used to be double bonded, it turns into a hydroxyl group. So we are going to be connecting the OH group in the chiral carbon that is the farthest away from the carbonyl, all the way with the carbon in the carbonyl, and then the oxygen that used to be double bonded is now going to convert to an OH. So for simplicity reasons, we can envision that ideally the hydrogen that used to be here may be connected to this oxygen at the end of the day. Now, these type of structures, other than being called cyclic Fischer projections, because it's the way that is illustrated here, they are also known because of a different type of illustration as Haworth projections. In a Haworth projection, overall, what we have is the same type of structure, meaning the cyclic monosaccharide, but now it actually looks like it's in a hexagon form. Moreover, one of the important things about Haworth projections is that it's illustrating an important feature of cyclic monosaccharides, and that is the creation of a new chiral center, which is right here. And this chiral center is known as the anomeric position. What I mean by this is that if we used to look at our original glucose molecule, based on the knowledge that you have for monosaccharides, you can detect that the glucose molecule has 1, 2, 3, 4 chiral centers. Upon cyclization, now your monosaccharide is going to have 1, 2, 3, 4, 5 chiral centers. So the cyclization process of connecting that OH to the carbonyl functionality creates a new chiral center. Moreover, when that anomeric position, which is ideally where most of the chemistry happens between monosaccharides, is going to have two different conformations that I will discuss in a moment. So how is it that we can actually create such structures? This is how we visualize the cyclization of monosaccharides. First, you get the structure of the Fischer projection of your monosaccharide, and we can see one illustrated right here. Then we are going to move this structure 90 degrees from left to right, and that is the illustration that you see here. Understand that the aldehyde, just for the purposes of this illustration, has been now converted to condense, and that is the CHO group that you observe right here. Next, we may see that there are some OH groups that are pointing up versus what they're pointing down. Overall, when you do the cyclization, as you can see, you have to bend the molecule. So the CHO group is right here. And we kind of create like a little boat. And then you can see that here is carbon 2, here is carbon 3, here is carbon 4, here's carbon 5, and this is carbon 6. Now, overall, remember that specifically, carbon 6 has to be connected to carbon 5, as we see in this illustration, but we have to put it in the appropriate position. So that's why we have to redraw the molecule where carbon 6 is now pointing in this direction, because you need to remember that the OH that is involved in the chemistry is this one. So we have to place it in such a way that now it is exposed to or in close proximity to the aldehyde that it's going to react with. So overall, what happens is that once we have arranged our molecule in the correct conformation, which is going to be this one, then we can envision that then the chemistry is going to be occurring between our OH group and our aldehyde or carbonyl functionality. Overall, what we can observe is that in the creation of this anomeric position, let me just redraw it. We are going to create that new chiral center that is called the anomeric position. But in addition, we are going to be creating a new type of functional group. So when we look at this molecule, because the creation of this center was created from an aldehyde reacting with an alcohol, the functional group that is created, and let me highlight it, which is this oxygen connected to a carbon. It is connected to this carbon chain. And I will mention what's the situation with the H and the OH in a moment. That is actually called a hemiacetal. This is not an ether. And the difference between a hemiacetal and an ether ideally is because the hemiacetal is formed from the reaction of an alcohol and a carbonyl functionality. It is not a type of functional group that is just sitting in a molecule. So understand that this specifically is going to be called a hemiacetal. Moreover, even though here in this drawing, you see that the H and the OH are just sitting next to one another, that is because in the positions, let me highlight them, here and here at the anomeric is where we place the H and the OH. Now, let's understand that there's different ways in which we can write the H and the OH. So let me just erase them for a moment and place them at the anomeric position. So when we have a carbohydrate that once the cyclization happens and the OH is pointing up and the hydrogen is pointing down, then that means that this is going to be a beta anomer for the type of conformation that has that carbohydrate. If on the other hand, you have an H on the top and an OH in the bottom, that is known as the alpha anomer in a sugar. To be honest with you, the reason why at the anomeric position that OH and H can be pointing up or down, it depends on how the OH attacks the carbonyl functionality. In a way, you can envision that if it attacks the carbonyl functionality from the top, then it pushes the OH group down. If, on the other hand, this OH group decides to attack this from the bottom, then it pushes that OH up. So that's why we have the difference in the anomers. One way that that I find useful to remember, how do I know that if I'm given a monosaccharide that is in its Haworth position, how do I know if it's alpha or beta? Then you can actually remember it by using the acronym BUDA. BUDA stands for beta. Let me just write it a little bit different. Beta up, down, alpha. So you simply look at the anomeric position, which is always going to be at this corner of the molecule. And if the OH is pointing up, that is the beta anomer. And if the OH at that position is pointing down, that is the alpha anomer. Let's proceed to talk about other types of reactions that involves monosaccharides. The next one that we're going to talk about is the formation of sugar alcohols. Understand that sugar alcohols are not going to be when you add sugar specifically to an alcohol solvent. So a sugar alcohol is going to be when upon reduction of a monosaccharide, you create this sugar alcohol. Sugar alcohols are actually used as sweeteners in many sugar-free products, because one of the things about sugar alcohols is that the body cannot process them. Our body can detect their sweetness, but these molecules are not utilized for energy. So here we have the synthesis of a particular sugar alcohol. This is specifically glucitol, or in other words, sorbitol. Now, we can observe that overall, we see the reduction reaction. And if we go back into the carbohydrates that are involved in the process, we can see that the aldehyde functional group turns into a primary alcohol. And we have seen such reactions before. And that is the only functional group that is affected in this reaction. Moreover, you can actually define what is going to be the name of your sugar alcohol by simply deleting the OSE ending in your monosaccharide name, and then you're going to put ITOL as the ending. Understand that sugar alcohols can also be synthesized from disaccharides and other molecules, but the same process is done. It is via reduction by doing a hydrogenation reaction, and the name is actually derived from taking the OSE out of the carbohydrate and adding ITOL. If we look at the label for the brand of sugar-free gum extra, we can see that sorbitol, or in other words, glucitol, is one of the sugar alcohols that is in there. But we can also observe that there is another one. As you can see here, we have mannitol. And by analysis, if we try to define, okay, what is the carbohydrate where mannitol comes from? So if our sugar alcohol is mannitol, then the carbohydrate that it comes from, remember, to revert the process, you remove the ITOL, and then the carbohydrate where mannitol comes from will be mannose. Another process that carbohydrates can undergo, and this is actually essentially in the body for us to produce energy from these important biomolecules, is through the process of hydrolysis. Now, hydrolysis is defined as the chemical breakdown of a compound due to the reaction with water. So if we look at the word hydrolysis, hydro is because of the water, lysis means to cut. When it comes to the different carbohydrates that we are studying in this course, understand that the only carbohydrate that cannot undergo hydrolysis is going to be monosaccharides. On the other hand, disaccharides are going to be hydrolyzed to two simple monosaccharides, because remember that if it's a disaccharide, it is made out of two single carbohydrate units. Next, if you have a polysaccharide, understand that you're going to get many, many, many units of monosaccharides. Now, the process of hydrolysis can happen via two different ways. You can see it illustrated in the arrows, but I would like to list them. Hydrolysis can occur when you react acid and water, or in our body, we actually have biomolecules that are called enzymes that are specifically designed to cut disaccharides and polysaccharides into simple monosaccharides. We already observed that monosaccharides can undergo reduction. In addition, they can also undergo oxidation. The way that they undergo oxidation is because these molecules have the carbonyl functionality aldehyde, they could convert that to a carboxylic acid. Now, there's a specific reagent that is called the Benedict's reagent, which is a copper-based reagent. It is important to note that when the Benedict's reagent it is exposed to a monosaccharide, what's going to occur is that the aldehyde in the monosaccharide is going to turn to a carboxylic acid, and that is the only functional group that is affected. In turn, you're going to produce copper 1 oxide, and since this is a brick red compound, it is an important way that we can detect glucose in a sample. Now, if a monosaccharide has the ability to convert copper 2 to copper 1 in a Benedict's reaction, then it is understood that that molecule is known as a reducing sugar. And it is called the reducing sugar because it can reduce copper 2 to copper 1, not because the sugar itself gets reduced, because we can obviously see that in the reaction itself, the sugar is actually oxidized because it goes from an aldehyde to a carboxylic acid. The last reaction, quote unquote, that I want to talk about is the creation of artificial sweeteners. So artificial sweeteners are going to be a variety of compounds that give you sweetness without the calories. They are chemical compounds that have been designed to replace sugars in diet, and they actually stimulate the receptors in the tongue to detect sweet flavors. I wanted to illustrate to you guys 3 commonly found artificial sweeteners that we have available. We can see that we have sucralose, which its market name is Splenda. We can see aspartame, which its market name is NutraSweet. And lastly, we have saccharin, and I believe that saccharin is sweet and low. Now, when it comes to these artificial sweeteners, we can actually observe that the only one that is carbohydrate derived is Splenda. Because in its structure, it actually resembles a carbohydrate. Splenda was actually synthesized from table sugar. And what happened to that table sugar is that it actually undergoes a chlorination reaction. How many chlorines does this table sugar was actually chlorinated with? 1, 2, and 3. So as you can observe, that is the difference between Splenda and table sugar, just those 3 chlorine positions that used to be hydroxides. Next, we have aspartame. And when it comes to aspartame, aspartame is similar to saccharin, are also known as non-carbohydrate derived artificial sweeteners. And the reason is because in their structures, they don't have or resemble the structure of a carbohydrate. Now, aspartame, different from saccharin, actually, it is derived from other biomolecules, specifically amino acids. And we're going to learn about amino acids later in the semester. So the amino acid aspartic acid and the amino acid phenylalanine were actually linked together to make this molecule. And at the end, a methyl group was added to create a methyl ester. And that's where aspartame comes from. Because aspartic acid and phenylalanine are the amino acids in aspartame, that's why sometimes in food products, you may see that if they contain aspartame, it says that phenylalanine is in the system. Because to date, there may be some individuals that have developed a allergy to phenylalanine, so it's important to put it on the food label. Lastly, we have saccharin. As you can see, saccharin overall does not look like a carbohydrate. Now, how sweet are these artificial sweeteners? Well, let's compare them to other carbohydrates that now we have at least heard of so far. So in this table, what we have is just relative sweetness of sugars and artificial sweeteners. What you need to see here is that this relationship is when you're assuming that table sugar, or in other words, sucrose, will get a value of 100. And then relative to that value of 100 that sucrose has, which we can observe right here, we're going to see how sweet things are on this scale. You can observe that out of monosaccharides and disaccharides, only fructose is sweeter than table sugar. All of the other disaccharides and monosaccharides represented in this table are less sweet. When it comes to the sugar alcohols, you can see that sorbitol, which actually comes from glucose, maltitol, which comes from maltose, and xylitol, which comes from xylose. What happens overall is that sorbitol and maltitol is less sweet than table sugar, but xylitol is actually as sweet as sugar alcohol. As sweet as sucrose. Lastly, when we look at our values for the artificial sweeteners, we can observe that when it comes to the scale, aspartame, saccharin, and sucralose, all of them are very sweet compared to table sugar, to the point that when you look at these numbers, you can see that aspartame is about 18,000 units, saccharin is about 45,000 units, and sucralose is about 60,000 units. So you can actually observe that these artificial sweeteners are at a higher, much higher level compared to table sugar.